Hey guys, I am Aditya C, head of the programming club in IIT Madras, and in this video, let's look at the solutions to CodeForces Round 804 Div 2. So let's get started with the first problem, the third three-number problem. We're given a positive integer n. The task is to find any three integers a, b, and c for which a is or b plus b is or c plus c is or a equals n, or determine that there are no such integers, where a and b, a is or b denotes the bitwise XOR of two numbers a and b. So just a small recap to what bitwise XOR is. So we know that any integer n can be written of the form b naught plus 2 power 1 b1 plus 2 power 2 b2 and so on. So basically we can write it as a sum of 2 power I bi, and we know that b0 b1 b2 so on is known as the binary representation of the number n, right? So and each of these is known as bits of the number n. So maybe not writing with this, bits will be represented this way: b n minus 1 dot dot b2 b0 b1 b0. So given a number like this would be the expansion of it. So for example, if you have n equal to 13, then the bits of 13 would be 1 1 0 1, basically 1 into 2 power 0 plus 0 into 2 power 1 plus 1 into 2 power 2 plus 1 into 2 power 3. Now for XOR, so suppose we have two numbers 13 and 10, 10 will be 1 0 1 0. So for XOR, we take the bitwise XOR for each bit of the numbers and just combine them. And XOR of two bits is 1 if they're different and 0 if they're same. These two are different, so it will be 1, this bit will be 1, this bit will be 1, and this bit will be 0. So the bitwise XOR of 13 and 10 will be 0 and 1, which is 7. So just a small property of bitwise XOR, 1 XOR 1 would be 0, 0 XOR 1 would be equal to 1, and 0 XOR 0 would also be equal to 0. So from this, now we have three numbers a, b, and c. For now, let's just imagine the three numbers to be a single bit number. So if they are single bit numbers, let's look at what happens. Let's just take this to be the bitwise XOR operator. So if we have a, b, and c, if all three are 1, then a is or b, b is or c, c is or a, all of them will be 0. The sum of these three would also be 0. If two of them are 1, a is or b would be 0, b is or c and a is or c would be 1, so the sum would turn out to be 2. If one of them is 1, then also the sum comes out to be 2, and if all of them are 0, then the sum comes out to be 0. So from this we can see that irrespective of what bit combination we take, the sum always turns out to be even. So we cannot have a solution if n is odd, right? Because whatever bit combination we take, we're always getting an even sum. And because we're going to do this for each bit, this sum will come out to be an even number. So because of that, the total number will also be even. Hence, if n is odd, we have no solution. So if n is odd, we'll just output -1. Now, what happens if n is even? So we can just try to work out something based on this. So we saw that in the case of 1 0 0, the sum came out to be 2. So instead of 1, let's just take some value small a. Suppose we have small a 0 0. In that case, a XOR b, which would just be a XOR 0, because 0 XOR 1 is 1, a XOR 0 would come out to be a. B XOR c will be 0 XOR 0, which will be 0, and c XOR a would be 0 XOR a, which will come out to be a. So sum will turn out to be 2a. Now, if the sum is equal to n, then one possible solution will be n by 2, 0, and 0. So this is one possible solution to this problem. If one of the numbers is n by 2 and the other two are 0, then a is or b would be n by 2, b is or c is 0, and c is or a would be n by 2, and the sum will turn out to be n, which is what I have also written here in the solution. So if n is even, we are outputting one possible solution of 0 0 n by 2 and returning, else we are outputting -1, because if n is odd, we just saw that there cannot be a solution. So this is not the only solution. We can even take n by 2 0. That is also one possible solution. Here we just need to give one possible solution, so we're printing n by 2 0 and 0. So that is the solution to problem A. Moving on to problem B. So problem B is almost ternary matrix. You are given two even integers n and m. Your task is to find any binary matrix A with n rows and m columns where every cell has exactly two neighbors with a different value than itself. So we need to make a matrix such that each cell has two neighbors that are not the same as itself, and the definition of neighbors has also been given. So let's first try to work out a solution for a 2 cross 2. So the solution that we have is black, white, white, black. So let's try to derive that. So let's say we put a black over here. There are only two neighbors to it, so both of them must be white. Now this white has only two neighbors, so both of them must be black. And now we have filled the 2 cross 2. Let's now try to extend the 2 cross 2 solution to a 2 cross 4, right? So yeah, all of these four had to be this configuration. Like once we fix this cell, the other three got fixed. So now let's see what happens in this 2 cross 4. Now this white already has two black neighbors, so this can't be a black neighbor, so we mark it white. Now this white needs two black neighbors, so we have to keep black and black over here. Now to finish the 2 cross 4, this black must have two white neighbors. This is BW, so we need to put a white over here. We were able to now finish 2 cross 4. Let's try to go for 2 cross 6. To extend this and go for 2 cross 6. Now similarly, this black already has two white neighbors, so we have to put a black over here. Now this black must have two white neighbors, so we put a W and W over here, and we get a B. Now if you try to extend again, you will end up getting WB BW, which is basically this unit cell. So we first had this 2 cross 2. From that we got this, from which we got this. Now this 2 cross 2 and this 2 cross 2 come out to be the same. So we started building, we had this one. From that we went to this one. And the third cell came out to be the same as the first 2 cross 2. So we can see that the whole pattern will just keep repeating. Now let's see what happens if we try to extend down. So if we extend down, we just add say 1 2 cross 2. So this white already has two black neighbors, so this has to be a white neighbor, and this white neighbor must have two black neighbors, so we put black and black. And now to finish the 2 cross 2, we put a W over here, which is WBBW, which is the same thing as this. And now we can extend this way as well. And so one nice thing is the conditions for this and this will get cleared up simultaneously. So for this cell already has two white neighbors, so you need to keep a black over here, and that does not affect the number of white neighbors of this cell. So you can do a BWWB, and this does not affect this row's solutions as well, because when you extend the whole thing, so you'll get WBBW, and this will come out to be BW. So when you fill the whole thing, you'll see that this row will come out to be the same as this row, which means it won't affect the number of non-equal neighbors of this row. And this we constructed independently, and this also satisfies the neighbor condition. So basically our solution is just alternating 2 cross 2s, where this is one of the types of 2 cross 2 and this is the other type. So let's call this type A and let's call this type B. We just need to have an alternating matrix like A, B, A, B, A, B, so on. And similarly in the bottom, here we'll have B, A, B, A, so on. Right, where A is this 2 cross 2 and B is this 2 cross 2. And so this way we will get what they mentioned in the question, that every cell has two neighbors to be its opposite color, and that will be taken care of in this 2 cross 2 itself. This already has two white neighbors, this already has two black neighbors, this has two black neighbors, this has two white neighbors, and this was constructed just to complement this, and the whole 2 cross 2s when extended, they form a nice pattern which satisfies the condition given in the question. Now coding this up can be a bit messy, but if we follow this AB thing, it becomes more neat. So if you see the indexing for this, so this will be indexed 0th row, first row, second row, third row, 0th row, first column, second column, third column. So when you number this, let's just take the leftmost corner of these two clusters. For 0 0 it is pattern A, for 2 0 it is pattern B, for 4 0 again it is pattern A, this is 2 0, this is 4 0, and for 6 0 pattern B, and similarly for so coding this up can be a little messy, but if we are careful we can do it nicely. So let's just look at when we get A 2 cluster and when we get B 2 cluster. So let's just focus on the leftmost cell in the 2 cluster. For 0 0 it was A, for 0 2 it is B, for 0 4 it is A, for 0 6 it is B, and so on. Similarly for 2 0, for this one it will come out to be B, for 4 0 it will come out to be A, because if we extend this down it will come out to be A, and so on. So if the sum of the coordinates of the leftmost index is a multiple of 4, then it is the 2 cluster will be of type A, else the 2 cluster will be of type B. So coming to the coding part, we can just get input of n and m and declare a matrix as shown. So for I equal to 0, I less than I plus equal to 2. So I indicates the row index of the leftmost element, and similarly j will indicate the column index, j equal to 0, j less than j plus 2. If the sum is divisible by 4, then it is 2 plus 2 of type A, which is BWWB, and we can assign accordingly 0 1 1 0, else we'll have to do 1 0 0 1, and after doing this assignment we can just print out the whole matrix, and this will be the solution to problem B. Now let's look at problem C, which is the third problem. So you are given a permutation of integers from 0 to n minus 1. The task is to find how many permutations are similar to permutation A. Two permutations are considered similar if for all intervals the max of A from L to R is the same as the max of B from L to R, where max is the minimum excluded element of the array. So it is defined as the smallest non-negative integer which does not occur in the collection. Max of 1 to 5 will be 0, and max of 0 1 2 4 5 is 3. Max is basically the minimum excluded element from the collection. We are asked to basically print the number of such permutations taken modulo 129 plus 7, right? So let's look at an example to this problem. Let's say this is array A and I want to build an array B. Now first thing is, the position of 0 is fixed in A and B. Why is that so? Let's say 0 does not occur over here. Consider this subarray in A and B. The max here would turn out to be 1, because the minimum number that's not present in the subarray is 1. But then if this element is non-zero, the max will be 0, which contradicts the statement given over here. Because of that, 0's position is fixed. This is the first observation. Now secondly, 1's position is also fixed. Why is that? Consider a subarray that starts at 0 and goes till the position of 1 over here. Note that 1 cannot occur anywhere in this bracketed part, because if 1 occurs over here, max of that part here will be more than 1, but the max here is 1, which cannot happen. Now 1 cannot occur in this part, but 1 must occur within this part, because the max of the array A over here is more than 1. So for that, 1 must occur within this whole part, but 1 cannot occur in this part, so 1 must occur over here. So because of this, the positions of 0 and 1 are fixed. Now let us talk about 2. We have two cases. One is if 2 occurs within the subarray bounded by 0 and 1. The second is if 2 occurs outside. So here 2 occurs inside. So let's say 2 occurs inside. Then I claim that 2 can occur anywhere in the empty space between 0 and 1. Now why is that? Consider the subarray that does not consist of 0. So any subarray within this bracketed part that does not have 0, max will be 0, so position of 2 doesn't matter. Now consider a subarray that has 0. and does not have 1. In that case, the max will be 1 irrespective of where 2 goes, because 1 is not present in the subarray, so max will be 1. Now consider this whole red bracketed subarray. For that, max will be more than 2 because 0, 1 and 2 are present here over here. So 2 cannot occur outside, because if 2 occurs outside this red part, then the max will be 2 for here, but the max is more than 2 over here. So because of that, 2 must occur within the bracketed part, but it can occur anywhere in these blank spaces. So if I call the right bound of this red bracketed subarray to be R and the left bound to be L, then R minus L plus 1 is the total size of the red bracketed subarray, minus 2 would be the number of blank spaces that I have over here. 2 is for 0 and 1 position. So these many positions are available for 2 to occupy. So 2 can take any of these positions. So the number of ways that 2 can sit would be these many ways. This is if 2 occurs within the subarray. If 2 does not occur within the red bracketed subarray, let's say 2 occurred over here and we had 8 over here, 2 is not occurring. In this case, I claim that 2's position is fixed. Why is that? Consider a subarray that does not have 2, something like this. In this case, the max of this array would be 2. Because of that, in B also, this whole part cannot have 2 in it, because the max of this part must be 2. Now consider this part. The max must be more than 2 for it, because 2 is included. So this part cannot have 2, but this whole part must have 2. So because of that, 2's position is fixed. So we saw that if 2 occurred outside, then its position is fixed, and we extended the bracketed region, right? Now let's see where we can place 3. We said that 2 could occur anywhere in this part, and this is the bracketed part that we had. Similar to 2, how 2 had to occur within this range, I claim that 3 also has to occur within this range. Reason is that if 3 goes out of this range, then max of this range here is more than 3, and it has to be more than 3 here as well, so 3 must occur within this range. And 3 can now occur anywhere within this range, because if I leave out 0, max turns out to be 0, which is independent of the position of 3. If I leave out 1, max turns out to be 1, which is independent of where I place 3 over here. So for any subarray in this region, the max will be 0 or 1 unless I take the whole thing. So 3 can come anywhere over here. So the number of ways to place 3 would be R minus L plus 1, total elements, minus 3 this time, because 0, 1 and 2 have already been placed. Now let's look at 4. 4 is a case of a number lying outside the region. So 4 is lying outside the region. Because of that, 4's position is fixed, because 4 cannot lie within this subarray, as max of this subarray is 4, but 4 has to lie within this subarray, because the max of this subarray cannot be 4. Because of that, 4's position gets fixed, and the bracketed region that we've been focusing on increases to this. Let's now take a generalized case where we already have a bracketed region like this, and so we have a bracketed region L to R, and all the numbers from 0 to x come in this range. Now when a number x plus 1 is introduced, if x plus 1 occurs within this range in array A, in that case it can occur anywhere within the empty spots in this range, and the number of empty spots would be R minus L plus 1, which is the total size of this range, minus all the elements that have been placed. That will be 0, 1, 2, 3, 4, which 0 to x means the number of elements that have been placed will be x plus 1. This happens when I am placing element x plus 1. When I am placing an element I in the region, it will be R minus L plus 1. Let's say I have already placed 0 to I minus 1, and I want to place element I. Here I will be equal to 5. In that case, the number of vacant spots I'll have is the total size of the bracketed region minus the number of numbers I've already placed, which will be I. So I'll have these many options for placing a 5 over here. So I can place 5 anywhere over here. Now when I encounter a number that lies outside the bracketed region, so for example, let's say I had 8 over here, so in that case its position is fixed. 8 has to come over here. So quantifying, if a number that we see right now when we are going from 0 to n minus 1, if a number occurs outside the range I've seen so far, then its position is fixed, else it can occur within any of the empty spots in the region. So let's look at the code to this. So first we are declaring vector a of n and p of n. So a of n is the permutation and p of n is an array such that p of I will store the position of I in array A. So for example, p of phi will turn out to be 4 because when you do zero indexing, phi occurs at position number 4. P of 4 will be 7 because position of 4 is 7. So if you see that way, I am taking input to array and I am fixing the position of number a of I to be I. After that, I am fixing answer to be 1 and the left range of my explored region. So I had explored, initially I would have just explored 0's position. So the left range of my explored position, left bound would be lft equal to p of 0 and rt equal to p of 0, and then I go from 1 to n minus 1. Now if the number I, the position of I occurs to the left of my explored region, if p of I is less than left, then its position is fixed, so and I change the range of the explored region. Else if it occurs to the right of the explored region, then again I change my explored region, I change rt to p of I and the position of I is fixed. Else the number can occur anywhere within the explored region. The size of the explored region is rt minus lft plus 1 minus I would have already placed some numbers in the explored region. Basically I would have placed I numbers in the explored region already, so I spots would have already been taken off. So those many choices are available for I to sit in the array, and then I am taking modulus modulo 189 plus 7 to ensure the answer comes out to be answer mod 189 plus 7. And after doing this for all numbers from 1 to n minus 1, I am outputting the answer. And this is the solution to problem C. So if you guys have any doubts and solutions to problems A, B and C, feel free to put it in the comments, and if you like the solutions, do like, share and subscribe. Thank you.